first talk for the day is by Siebert from UT Austin, and he's going to tell us about periods and analyticity in toric degenerations.
Yeah, I'm excited to be back to Miami. It's always nice to come here. So this is the opposite of Janke's inspiring talk from yesterday. So he started off saying, well, it's all great ideas and but not quite work out. This is the opposite in the sense that sometimes you have to clean up your desk, you know, and then you find something interesting and you still want to share it. So that's this kind of talk. And this is actually, it's a long story, especially about that part that is completely new. So this is paper on the archive from 2014. It's all joint work with Helge Woodard. Something with canonical coordinates and toric degenerations. That paper was rushed out a little. I mean, you know how things goes. Young people need publications to apply and stuff. And we haven't actually submitted the paper anywhere because we felt this still needs to be cleaned up and so on. And now we're going through the finish line. So the proofs are much nicer, the statements are nicer, and there is a very strong application, which is analyticity, which I've claimed should be true for many years, and now we can actually prove it. Okay, so what's the setup? In toric degenerations, we start with an x0, which is a union of toric varieties. So let's call these x sigma, and the sigma will be the momentum total. So there's always a momentum map that will have some meaning in a minute. And then there's a procedure. These white flows are really small, right? Maybe I should. Well, there's a procedure to produce well, first formal family maybe. Actually, it will be important to have something slightly bigger here. So there's a coefficient ring, A. I will describe later. And there's a canonical procedure to produce these things by some wall structure. So the best reference these days to look at these, if you're scared of all these papers that Mark and I have written and other people have written on the subject, look in the theta functions paper. That's a long paper, but it should be very accessible. The procedure itself, if you don't care on how to get the wall structure, is actually quite simple. And I think everybody can easily, in a few hours, understand how this goes. Okay, so what's the wall structure? This lives on the union of the sigma with the topological manifold, cell complex, and the walls look, for example, like this. One of my favorite examples. It's a P2, so it would be the xt for t non-zero, which doesn't quite make sense in the way I've written it. But we will see that it is actually analytic. So if you have an analytic family that's a P2 and then it has a pair, there's an elliptic curve embedded, a smooth elliptic curve, ET, that's actually the Tate curve. So that would be my B. And I subdivide it in this way. And then I put these affine singularities here that are not so relevant at the moment. And then there's a wall structure.
Maybe you can say more, but what is ET? In what sense is that a toric variety?
Sorry, say it again. ET is not a toric variety, no. What do you mean?
So
I'm just saying, let me just say this. So the B looks like this. It's union of three these triangles. There's a wall structure that is actually everywhere dense. It all emanates from the origin, essentially. It goes through here, huge mess. And then what I'm saying is, in the family that you produce, So x0 is a union of 3 copies of these weighted p2s. And then you get a family x, and the general fiber xt for t non-zero is a p2 with an embedded Tate curve for t non-zero. So that's a c star mod t. Okay, so the good thing about this talk is the wall structures will not appear at all. Okay?
And the curve is degenerating to the intersection of the triplet?
That is a Tate curve. So if you restrict the family to this ET, it becomes a Tate curve. So it's with the three gone, narrow 3 gone on central fiber. Yeah, so these walls will never appear from now on. I will just say they are there, and you have to take care of them in the proofs, but they don't appear in the statement, they don't appear anywhere. Okay, so then what will be important, the only thing that will be important here, the whole computation, all the arguments, except some stuff that is in black box, all these period computations happen away from codimension 2. So the only thing we need to understand is the codimension 1 locus. So in codimension 1...
So you mean you have some general theorems which take care of the codimension 2 stuff? And then you don't worry about it?
Well, codimension 2, actually, you have to still do something, but yeah, essentially, right. Not for the wall structure, but for the construction of the family and the periods. These periods. Okay, so in codimension 1, the situation is like this. So you would have these some maximal cell x sigma prime and x sigma. And you take trivial deformations of these things. So that would be, for example, in 1 dimensions with trivial parameter, just cross C double bracket T, something like this. And then you have something in the middle, that's the codimension 1 locus. And this has these model deformation. So I'm writing down, I'm sometimes mixing the geometric and the picture in X and the picture in B, but hopefully you know what I mean when I'm drawing pictures. So these are monomials, Z plus Z minus, pointing into these two neighboring components. And the equation is, the local equation in codimension 1 is Z plus Z minus is F rho times T2 kappa rho. What does this mean?
And these monomials are encoded how?
Say it again.
How are the monomials encoded in this picture?
Well, that's just toric geometry, right? So the monomials, this is a momentum polytope.
Yeah.
So any tangent vector gives you a monomial.
But do I choose one, or
Do I what?
do I choose a tangent vector to that?
Right, the Z plus, Z minus are ambiguous up to a choice, up to monomials on this double locus, okay? But that equation, I mean, the ring you get is the acanonical isomorphic, right? Up to this choice.
So sorry, you choose one.
You choose one, right?
Sorry, can you say one more time, what is that ET in terms of the X0, like in terms of that diagram you drew on the first board, where does ET appear?
So if you look at this momentum polytope here, each of the momentum has this line, it's a divisor, right? It's a P1. So you see here a union of 3 P1s that gives this neuron 3 God.
Oh, that's the
That's the central fiber of the Tate curves that would appear here in the degeneration of the ETs. Okay? So when you run the program for B with boundary, you get a divisor in your family. And in good cases, that's a part of the program itself, like in this case. It's actually a straight line here, if you do it properly. Anyway, that's just to give you some idea. It won't be important for its talk. So what's the F rho? So the F rho is the most interesting piece of this information. Actually, it depends on T. The T itself contains all the higher order information along this codimension 1 locus. So this is it's in the monomial, in the Laurent polynomial ring in n-1 variables. These are the monomials along the double locus, and then you have a T. Okay, so intrinsically this is C of lambda rho. where lambda rho, these are the integral tangent vectors along rho. So there will sometimes be lambdas, capital lambdas, capital lambdas coming up. These are always the integral tangent vectors. Okay, so maybe the first, and there's one more information. So that gives us, and then you kind of glue torically. And that is some information I typically sweep under the carpet when giving talks, but will be very important later on. You can twist these gluings by torically, by toric automorphisms of these pieces. And they are given by what we denote, so if this is a rho is the notation always for coordinate one lower side. So that's S sigma rho, and that would be, sorry, that's here. So this means that that's called a gluing data. So that maps Z to M. Maybe I should start here. So let's say we take a monomial here, Z to M, and that doesn't get mapped to Z to M on this thing here, but it goes to S sigma rho of M times Z to M. So S sigma rho is a homomorphism from lambda sigma to C star. Yeah?
And how is that encoded in this?
It's not encoded, it's additional data. But we will have universal choices of this, okay? That will come up.
So you choose one for each?
At the moment, it's an additional, right. Yes, and there's some compatibility.
Oh, it's a cancer.
It's your homology class. Okay, so then there's another piece that is very important for what's following. It's the long singular locus. So if you look at this equation, it looks like normal crossings except at the locus where f rho is 0. That's a kind of bad locus, or actually the interesting locus. So that gives you a codimension 2 subset union of hypersurface on the singular locus of x0. So you take f rho equals 0, and that sits in x0, actually in the singular locus. So that's codimension 2. I haven't told you, I mean, you take closures, of course. The f rows do extend it. And then you have some degenerate moment map. Might be interesting to symplectic geometers here. It's called momentum map. You know, if all the S sigma rows are 1, trivial, you just put together your momentum maps, you get a global momentum map. But it will be important to also understand the cases where S sigma rho is non-trivial. And then you can use theta functions and the Fubini-Studi metric for the theta functions to actually globalize, generalize this construction to a global momentum map. So there is this such a map mu constructed by theta functions that is a momentum map when restricted to any x sigma. So that is an honest momentum map for the local U1 to N action on x sigma for the restriction of the Fubini-Studi metric. That's an honest momentum map. Okay? So it's like a degenerate SYZ vibration.
Can I just maybe I missed it? This F rho, how? I mean, I'm saying, how is the choice of this F rho encoded and what's happening?
There's a unique choice once the singularities are simple. Otherwise, it's part of the wall structure.
Okay.
So it's highly non-trivial, for example, in these Grosser-Kiel constructions. Okay, so and then the cool thing that I only observed thinking about these period integrals is that there is not only a kind of discrete affine structure, but there's a natural affine structure on the complement of the momentum map image of Z. So that's so there's a natural affine structure, integral affine structure. Oops. on B minus A, and A is the amoeba image, so the image on the momentum map of Z. Yeah? So that's a union of amoeba on these codimension 1 low cells. That goes as follows. So you know, there's a natural reference structure on each of these maximal cells, and then essentially you have to tell when is a line straight. So how do you parallel transport? So there was this question, how do you choose Z minus Z plus, okay? So essentially, one of the choices is arbitrary, but then the other one should be straight, okay? Otherwise this equation changes by a monomial along row. So how do we see when something is straight? Well, take any such model, any Z plus Z minus, you get an F row that changes by monomials. But then you look at the restriction of ref row on a fiber of the momentum map at a point x. Yeah? So I'm crossing this row now, and I want to know how much do I miss from these monomials to be straight. Yeah? So I would like to find this out. And how do we see this? Well, once I restrict, I get a map from intrinsically that's a lambda x dual tensor U1, and then it has no zeros, right? Because we're away from 0. So for x not in A, get the following, I get a map to C star, and then I take the argument that gives a map to S1. So here, this is nothing but an element of lambda x. Okay, so that thing is an element of lambda x, and let's call it mx. And then what this is, let's see, direction that you get for the monomial Z minus times Z2 minus x. Okay? So now there's, at any point of the double locus, there's a natural way to write these things by correcting F row by Z2 minus mx. And that will make Z2 minus mx F row will be contractible. Yeah? It's a map a priori to C star, but now it's a map to C star that doesn't encircle the origin. That will be very important later on. Okay, so let's look at some examples. So those people who haven't seen this actually have something to hold on to. So let's look at some two-dimensional example where I just have some C star, so my row that has an X row is a C star. Well, then there might or might not be vertices here. But, anyway, so I'm taking F row to be, let's say, 1 minus W times 1 plus 2W, okay? Then the amoeba image, well, it has zeros as W equal 1. Yeah, so this is a kind of W direction, and minus 1/2. Okay, so what are the good choices? Well, if you're here, F row is close to 1, so then you just take F row. Here the natural choice is F row times W inverse. Yeah, and then here's F row times W to the minus 2. Okay, so what does this look like? If you think of an SYZ fibration over the thing, generate SYZ fibration and deform to the general fiber, there are these circles of radii 1 and 1/2. And these are the two bad points. So these are the fibers of the restriction of the momentum map to this row.
What is the zero fiber?
What do you mean zero fiber?
No.
Zero fiber of what?
Of definition.
Oh, this is just a picture. Okay. At the moment, I'm just talking about x0.
Okay.
For quite a time, I will just talk about x0.
And what is x0?
X0 in this case is a union of two copies of C star cross C. That's a C star, and I didn't say this yet. Maybe I should have drawn something like this, okay? That's my X, my B. Okay, so I have two cells coming together.
Two copies of C star cross C along
C star.
Along C star. And the singular point is something you chose, or?
Right, by F row, I'm choosing F row. I'm just saying whenever I'm two-dimensional, right, the only thing I have is this equation, right? So I have something toric. This is my C of W to plus minus 1. And then two more variables, C plus C minus and the deformation variable T. So let's forget about T. And then it's just determined by F row.
Just so I have some intuition for what's going on. If I did deform this, what would I get?
If I do what?
If you did deform this.
Oh yeah, just the equation, right? So it's just C plus C minus F row times T.
What is that? Okay.
It will be fibered over this diagram with two singular fibers I mean, one of those things I can tell you is actually a C2 because you can eliminate. Well, if I have one more, I don't know, some logic or whatever. What is it?
It's probably close to an A and fiber.
Yeah, it's an A, right. It's a smoothing of an A2 kind of thing, yes.
Another medium is that you would expect the zeros of F row will be grown to different powers of T.
Sorry, what was this?
In non-Archimedean SYC, which we used to
Mhm.
let us see that zeros kind of single points on this image too, they behave like different powers of T.
Yes.
Yeah, and here there's no T, it's kind of 1 and 2.
Yeah, you could decorate this with T or anything else. You can do that too.
A T square object. So.
Yeah. Right.
So can you say one more time what that SYZ base picture was?
Well, that is just no. This is not the SYZ base picture. Sorry, this is actually X row. What I wrote X row. So that's just C star. Okay, so it's just a W coordinate, the W plane. Okay, so and then maybe more interestingly, in dimension 2 is kind of boring, right? Dimension 2 is very interesting, but it's kind of boring because you just have these points. But in dimension 3, you get all these incredibly interesting pictures. So let's take the mirror of local P2. It's another of my favorite examples. The green seems to stick. Strange. Okay. So that is that picture. So you take, well, that's actually codimension 1 locus. So the real picture looks like this. It's a double tetrahedron. So that's the example is discussed at length in the ISM proceedings. And then yeah, so that's the mirror of local P2. And then the function f rho in this case, so let's say these are x and y, and then you have a z coordinate maybe here. And I'm just writing down what f rho is in this case. So that would be one row, right? So f rho here is 1 plus x plus y plus 1, actually no, t over x, y. And then maybe optionally, we would insist to put a g of t here. So you can write this as an infinite product, but for the computation that I'm going to present, you can work with any f rho here. So what's the amoeba image of this thing? What's the A? Well, it's a union of amoebas of a line on each of these things. Well, actually, it's not an accurate picture. These are actually round, but it looks much easier and much nicer like this. Okay? So think of an amoeba of a line, and then kind of diffeomorphically squeeze it into this triangle. That's the picture that you get. Okay. So and then that equation would be the right thing actually when you compute f rho here. If you compute f rho here, the natural thing is you would have to multiply it by what is it, y inverse.
What does it mean, compute f rho? I thought f rho was something.
Sorry, I told you that there is a kind of natural way to write this.
Just this correction.
Yeah, with the correction z to minus mx correction. Yeah?
And the correction, it changes in different components of the complex.
Exactly, because it's this kind of, this zero locus of f rho, it changes as the zero locus of the amoeba image of f rho. Yeah? So if you compute the mx here, let's say you compute mx here, then you would find, I think it should be minus 1, 0. Or minus 1, 0, 0, depending on your choices, of course.
And this thing is what you called A before, this green thing?
Yeah, the green thing is the 8. That's it. Okay, so so the aim is now to compute the following thing. I want to take certain n cycles on x0, and then, well, there's a way to kind of deform them to the T fiber, yeah, which is unique up to adding vanishing cycles. And then I want to integrate the canonical n form that the construction comes with, which is just on each component is a d log z1, which d log zn. I mean, that has to do with the fact that all these wall crossing morphisms are holomorphic volume form preserved on here. So that I would like to compute. And I'm taking a class of cycles that's different from what Shield talked about. Is a class of cycles which behave like log t. So there will be a function g, and then a polynomial function h, and then times log t. So, and the point is that if I truncate, so actually, if in working with this, we have a formal spectrum. It's a little bad to work with, infinite constructions. So what you, in practice, what you do is you truncate at a finite order, okay? And I want to make sense of this integral at finite order, although here's a log t term, okay? That sounds a bit funny. So we truncate, so x mod t to k plus 1, let me just write it like this. It's a base change. It's xk, and that lives over spec. It's now an honest scheme over spec ct mod t to k plus 1. And I want to compute this. And then I want to, in this case, I want to say, I want to find, in this situation, I want to find g and h up to order k plus 1. Okay, so the first improvement over what's on the archive is that we have been a lot more careful in thinking on how to make this work. So there is actually a definition and a theorem saying that such a notion exists. So we define this carefully and show that it has all the expected properties. So if xk, or if your x actually comes from an analytic family, that will be the computation to order k, okay? And there is a notion that you can define the g and h, and then if you change beta 0 by homology, you get the same result.
So
okay.
this beta naught is mirrored to the structure shape of a curve or something?
No.
No, I think it's BT0, it's kind of project to a graph.
Yeah, I will say in a second. It's S1, it's the one that gives canonical coordinates, it's E. So it can be defined. Okay, let me just put it this way. Okay, so let's come to the construction of beta 0. So the beta zeros we're going to look at, as I just mentioned, is they are fibered by S1 to n-1 bundles, n-1 torus bundles over graph and B. So you have all kinds of natural end cycles that you construct in such a situation, right? The most obvious one is take a point, you take the fiber, that's in this 1 to n. Totally trivial, you know what the integral is, it gets 2 pi to n. Okay, so the next case is the case I'm looking at, and the most difficult one, so to speak, is the one that Sheil was talking about, is where you have actually a section. Okay, but then whenever you have a tropical cycle, anything close to that, you can actually produce such end cycles. Okay, so what's a graph? So we start by taking a sheaf-valued homology, singular cycle on B minus A, with values in this local system. I shouldn't write too far down, right? Local system of integral tangent vectors. Yeah, it's locally free on B minus A. So let's call this beta trop.
Well, what is C1?
Chains, singular chains. Okay, they just carry a section of the local system. Okay, so the notation will be these beta trops. They will have edges E that I think of embedded for simplicity in B, and then they have a tangent vector psi E in lambda restricted to E. Okay, and you just parallel transpose, and then of course you assume that the edges maybe just lie in one of the sets. Okay, so then you can look at what you get, and there's one thing. I mean, in not moving into A, actually don't lose it much. It comes from the following proposition, simple proposition that says that if you look at C1 of B minus A lambda, there's a natural map to H1B Yoda lowest lambda. So what is this? So A often, typically, always contracts to something like a skeleton, yeah? So let's take the skeleton to be delta. It's a skeleton of A. And then the iota is the inclusion of the complement. Okay, away from the skeleton of A, of course, you have an extension of this affine structure, and then you get this homology group, which is much nicer. It's like a polyhedral kind of homology, and that thing. So the statement is that this is surjective. And these are the groups that we actually can compute and that relate nicely to the complex geometry that we will see.
So you're saying H1 of B with coefficients in this sheaf is basically H1 of the local degenerate fiber?
Sorry, again, is basically?
No, because it's local system of just take each one.
Outside the scope, yeah.
Yeah.
That's known to be the H1 of the neo.
No, that's not. No, that's not true. Actually,
Okay.
It depends on the kind of
Yeah, but in
singularity.
fact, in our very old paper, we already considered the spirit maps here, complement could dimension to local sense. This is fine structure.
What do you mean?
No, we have the spirit maps, period integration of graphs, and this the same stuff. Time ago. Maybe in a special example.
You mean for in the K3 paper? or-
Yeah, but we discussed very general picture.
Right. But yeah. Okay, so so then there's let's look at one. Let me see. Do I have time for these?
Can you draw on this picture what I should imagine a C1 as a J?
Right, I'm about to do that. Actually, maybe not in this picture. Yeah, let me do the other picture, which is kind of much easier because it's kind of interesting. Let me take another. Okay, so let's look at this thing. There's these two singularities, focus singularities. So one good way to write this, it's already in Simon's papers, is to write a fundamental domain of the affine structure. So the model drawing around these singular points is of the form 1, 1, 0, 1. So it leaves in vertical vector invariant while it moves such a vector around. Gives it a little shift, shear transformation. So then you can write a cycle. Well, now I have to concentrate. There are essentially 8 signs. And sure enough, I can never remember what's the right one.
So in this picture, there's no amoeba.
The amoeba are these points. Sorry.
But
They're just points. I mean, in dimension 1, dimension 2, they're always points of equipment. So I'm taking this one. There are many ways to write this. Essentially, there are 2 different ways. One that gives a trivial result, the other one is interesting. So I'm trying to write down the interesting one. So what are my xi's? I want to take the psi here to be 0, 1. Yeah, so this goes up. And then here I'm taking that one. And if you parallel transport it through this thing here, you get that one. And then you have 2 more here. So up here I want to take that one. And down here you take that one. Okay? And then, of course, here you have some co-cycle conditions. So, for example, here, let's just do the exercise. Going in leaves it invariant. Going out changes signs. Sorry, that's something wrong, of course. No, going in leaves it. Okay. Yeah, so this is zero tension. Now, what is this? So that's a cycle. Okay.
So again, this looks to me like a 2-dimensional cycle.
It will be.
It will be. Okay. And what confuses me is why are we taking C1 coefficients in lambda? That should be like more like the
You will see in a second.
n minus first. Okay.
I take the perp. Okay, so then how do we construct now the end cycle? That's it. It's a Lagrangian, yeah. Will be a Lagrangian.
Yeah.
Okay, so so how do we construct from this tropical cycle an end cycle on x0? So we're just doing stuff on x0. Yeah, so what you do is the following. So over each sigma, so you know you have some edge E, and then you have this x sigma favored by n cycles, n tori over this thing, and you take a section. So there may not be a global section of your SYZ vibration, but there always is a section over a graph. Yeah. So let's call it SE. It's a section. Yeah. And then the way to produce the cycle is simply taking the orbit and then S1 to n minus 1 action. So that's an orbit under U1 to n minus 1. So how do I get this U1 to n minus 1? Well, if you look at the tangent vector, any tangent vector in a momentum particle, it really avoids the green, as beautiful as it is. So if I look at psi e, and you take the perp, okay, that defines that sits inside. Sorry, so the perp tensor U1 that sits in lambda dual tensor U1. Okay, and that's a torus acting. Yeah, so that guy is the U1 to n acting on x sigma. Okay, so this thing is an isomorphic to U1 to n minus 1. Okay? And then what do we do at the vertices? Well, at the vertices, the balancing condition tells you that these U1 to n minus 1 orbits sum up to 0. Yeah? So we have a bunch of things coming in or going out at a vertex. And then you take the sum plus minus of these orbits, psi e perp as cycles tensor U1. Let me just write it as D. Okay, so that thing, let me call this, that gives beta E, yeah? So then we have somewhat plus minus beta E that's 0 in n minus 1 homology of the fiber. Okay, and then you can fill in. It won't matter how you fill in. It's just that differs only by vanishing cycle. Okay. So then I'm ready to state the main theorem. And it will take a little while to explain the terms in the main theorem, but it's a very clean statement. Much cleaner than what's on the web at the moment. So the main theorem is as follows. The integral beta omega, do I want to state it in the, maybe I want to state it in the exponential form. Get rid of the logarithms. So the x of 1 over 2 pi I to n minus 1 integral beta omega, that is, it has first a term that I write s comma beta trop. Then there's a term that you expect, there's a t, and the power has something to do with our kappa rows that we had in the beginning. And then there's another interesting term that I just denote r at the moment, okay? XR, actually, I mean. So what are these terms? Let's start with the, so these, you see that these two terms have nothing to do with our f rows. It's totally kind of discrete. Well, except this gluing data that appear here, okay?
So we're not supposed to yet know what is S and what is C1.
Well, I'm going on. I mean, the S has something, you kind of know the S. So the S is a collection of S row sigma, okay? S sigma rows. These are the gluing data, yeah? So how do I pair S with beta trop? Well, whenever you cross a row, you have one S sigma row here, or that's the S sigma prime row, and here you have the S sigma row. And the contribution to S sigma, the contribution to S beta trop is a quotient. Well, sorry. You also have a tangent vector psi e that you carry through. And then the psi e pairs with some primitive normal vector. Let's call this d rho. So this has an orientation, right? So let's call this d rho check larger 0, d rho check lower 0, smaller than 0. This is a primitive normal vector. So I compare this with psi e. That tells you essentially how parallel you are from rho. Okay, that's just an integer. And then you take the, sorry, that's the power. And then you take the S sigma prime row over S sigma row, and I hope I got the signs right. Signs are actually no. No, it is correct. Okay. Similar for C15 beta trop. Okay. So no, this is just an element of C star. Yeah, that's some number, some scalar. And then what is this C15 beta trop? Well, that's similar. I'm not going to tell you why I'm writing C15. Some of you have read some papers.
This is an integer, yeah.
That's an integer, right? And that's an integer. And the C15 that's just a sum, again with these kind of things decorated. D row check, psi e, and then we have all these kappa rows that we crossed, right? They appeared as exponent in Z plus C minus is F row times T2 kappa row. Yeah, so remember that. So that's part of the data encoded in this phi. Phi is essentially a collection of all these kappa rows. Note that this computes the topological monodromy of your beta. Okay, so this thing, so the Picot that has a Picot-Lefschetz transformation for beta t. And that's exactly what you expect to get for the t behavior. That comes from the log t. Yeah? So the Picot-Lefschetz would map the beta t to C1 phi beta trop times f, and that's an SYZ fiber, the vanishing cycle, plus beta t. Yeah, that's a Picot-Lefschetz transformation.
So can we go back to the previous term? So that you're supposed to take sum over all rows, or?
It's a product.
Sorry,
Double-
sorry, yeah, of course. This product of all.
So then maybe the most interesting term is the XBAR. Okay, without explaining what the XBAR is, doesn't make sense at all. Right? So the R disappears in the best cases of our program for what we say like simple singularities or normalized or whatever. But for example, it doesn't disappear for the example of local P2 I showed you with if you do not include the G of T term, the mirror of local P2. So the R is a complex, what I call the complex Rankine function. So the Rankine function appears when you try to construct the skeleton of an amoeba. Yeah, so you know an amoeba contains a tropical curve, tropical hypersurface, and that's obtained by looking at the Rankine function that integrates something like the logarithm of the absolute value of the f rows. And
is it a function of t or?
it depends on t, yes, because the f row depends on t. So the Rankine function is again a sum over all these rows that you, or all the vertices actually I should say. It shouldn't be. Yeah. Did I say anything? No, I didn't decorate. Okay. So it's a sum over contributions of these f rows. The versions of f row at a vertex. I haven't said what this is, but let's just put f row comma v. Sorry, I should change this, otherwise it won't make sense. Z2 minus mv. That's a vertex. So it goes over all vertices that pass rows, yeah? And then you have a v here. Maybe. So what is this function? That function is the integral. Let's see. I have a 1 over 2 pi r, right? Do I? Something like this. 2 pi n minus 1, right? Yeah, I think x, right. That's correct. So, and then you integrate over an n minus 1 torus. The fiber of this moment map restricted to your hypersurface, to your C star to n. Yeah, and then you have a logarithm of z to mb f row, and then you take d log theta 1, d log z1, and so on, which is the same as d theta 1 d theta n in polar coordinates. Okay? So if you take the real part of this Rankine function, the real part of it, the real part of the thing here, that appears in the that's a traditional Rankine function. And typically it's on the complement of the amoeba, it's an affine function, yeah, with integral slopes. But here, because it's contractible on the we said that this is contractible on mu minus 1v. It's actually a constant function. Okay, so it doesn't matter. It's a constant function on your component. So it doesn't matter if you wiggle a little bit with your v, the crossing point of your point. So that is important thing. So here this is locally constant. No, you won't be able to see this. Okay, so that's about it. I think I've only 10 minutes, so I need to go to analyticity. Let me just say, yeah. So this is, yeah. So for example, I mean, let me just say the following. So if you do this, if you do it for this mirror of local P2, we have this example here, right? And you kind of see a tropical curve here, yeah? Not quite because it goes through the singularities, but trust me that you can move it away and then kind of have a little circle around it. If you do the computation, you will see that you can extract the g of t. Yeah? So you remember we had these f rho is 1 plus x plus y plus t over xy, which does not power series product expand, but you can write it as an infinite product. And so on. Once you add the g of t. And this g of t can be computed by the integral. So this is exactly saying that we have canonical coordinates once we put in the d of t. Once you have this formula, there are many core applications. For example, it tells you what are integral classes. Yeah, what are integral classes? You can extract the integral. So let's say for K3 surfaces, you can compute the Picard lattice. You know, there's this S. So when is something? When does a class stay integral? A homology class, a Poincare dual of a homology class. When is it a 1-1 class? Well, if this vanishes, right? So it must be the perm of C1 phi. That's something homological. And that thing here has to be 1. So there can be cases where the S is not equal to 1, whereas this is 1. So you get all kinds of interesting things where you get families of K3 surfaces with prescribed Picard lattices constructed from the program.
So this ability to follow integral classes, does that cause you to believe this will never work in a higher dimension? I mean, I'll say over.
What do you mean? It does work in higher dimension?
No, when you have not a graph, but.
It won't be that simple. I'm sure there's a similar. I'm sure one can compute it, but yeah, we're not there.
If you compute it, you could Plochkin conjecture, right?
Sorry, what?
If you compute it, you can do Plochkin conjecture.
How that?
You know which classes will.
Oh, you don't. Well, you won't get all classes this way.
Flat coordinates, this R doesn't have that
Sorry, say it again.
in flat coordinates on the mirror map R should be constant.
Once you take your F rows normalized,
Yeah.
what we call normalized. So you want these, yeah. Then it doesn't depend. That disappears, right? This disappears once you can write this as an infinite product.
Yeah.
Then you get all these oscillating integrals to 0. Yeah. So this is,
If you don't get all classes, how can you get something that specifies the Picard lattice?
well, for dimension 2, I get all classes. It's coming. Okay, let me rush to the analyticity. Just enough time to sketch. To give you a flavor of our struggle for many years. Well, not all the time, but on and off. So that works only if we have rigid singularities. A little better than what we call simple, so something like locally simple. Some technical condition. It means in dimension 2, it would mean you really only have these singularities where the monodromy is 1, 1, 0, 1. Otherwise, too much topology disappears in the singularities. Okay? And then we get something like a universal family, and now I will be very precise of what this means universal. It's not quite universal the way I'm writing it, but okay. So you have an X to spec formal A double bracket T. So the A has something to do with the affine cohomology. It's a Laurent series ring on H1 B, Yoda star lower star lambda checks the dual of lambda. Then dualized, okay? So that kind of carries, maybe we can roughly see how this comes about. It carries like universal gluing data, yeah? So this is like the universal gluing data. And it will be enough to work with one period. There's a similar story where you can replace this with some higher one in it, but it's a kind of trivial extension of the subject. This makes it harder to think about. Okay, so and then the theorem is easy to state. So now we have this family over a kind of formal extension. The A is this polynomials, yeah. So there's a torus of some possibly high dimension. Let's say for K3 it's 20 dimensional, and then you have this formal parameter. So what we can prove is the following: there exists an analytic family, flat of course, and so on. X to, let me write it, U cross D. And U is contained, I'm writing spec, I mean the analytic, the complex space associated to the spec. And that is the C of H1, right? Spec A. Spec A. That's an analytic open, later on. So it's an open subset, D is a disk. Such that they, so actually for any point X in the fiber, right? Any closed point, closed. Such that the completion at this point, so at the point X, that is now over spec form of the completion of A of X at the point X of T, that is isomorphic for this family, the completion of X at the point X. Yeah, so again, completion at X. Okay, so in particular, this means there is an analytic family where your, of course, your period integrals are monomial. Okay. So I think that's reassuring that what we produce in canonical coordinates, these kind of strange models that actually are just kind of finite order approximations of an honest analytic picture. So it might be useful for symplectic, should be useful for symplectic applications of this. So there are quite a number of steps.
So again, you said it lives in U cross, over U cross D?
Yes.
What is this? I thought,
Were you confused?
no, I'm just.
U is an open subset of the torus in the fibers. It's a big C star to something. Okay. And the D is which has a T parameter, right?
So this is saying you get convergence but not uniformly in the point A or something. Is that right? Or
Yeah, I think the problem will be, right, the arguments, yeah, we decided not to include it. There might be more, but there are some stacking issues with automorphisms in this direction. That
I think the reason that's because I thought U is going to be U is the base model living data.
no, it's not all, right? It's an open subset of the green data. Okay. Yeah. So the first thing is, we're kind of, if you compute period integrals, and the formula is still here, you will see that there is actually a GM action on the thing that acts by order weight 1 here and by some negative weight here. So obviously period integral will stay invariant. And we want to use period integrals to get coordinates on the thing. So apparently we can only get coordinates on a slice. There's a subtle difference between ordinary deformation and log deformation. It's essentially rescaling T means you change the log structure on the base. I spare you any discussion of this. We have to cut it down. Yeah. So the first step is there's a GM action on X, and then we take a slice. Yeah. So the GM action essentially looks like this. It's free on it acts by a subtorus on the central fiber of the base. Yeah, that's a base, and then I take a slice. That's a slice. Okay, so that's the first step, and then we compute the periods. So this X bar is now disappears because we are rigid. The X bar disappears, so it turns out that the X of 2 pi I. Sorry. should finish here. So the x2 pi integral beta omega is S to some dual of the beta chop. These are coordinates along EA. Okay, and then you have some t power, that's just a C1 phi beta chops that we have before. Okay. Yeah, so let me come to an end. So then the other steps are, there are a number of difficulties now. So goes like 3, 4, 5. We have to approximate analytically. We get an x such that with the same period integrals. So period integrals make always sense for these cycles. We have cycles on x0, we can extend, we can compute. So the same period integrals. Then you need some statement that these period integrals actually give you coordinates. So that's a kind of a perfect pairing. You need to prove something in affine homology. Plus you need, yeah, no, that's okay. Affine homology, that means we have coordinates. Periods give coordinates. So then the way it works, so now we have two families that have the same period integrals. Now the argument is that if we complete at a point, we get a formal deformation problem, okay, like Schlesinger type kind of thing. So we have to prove that both are Hull. Then we get that there is more below the base. And how do we prove this? So both x check, x hat and x hat are Hulls. Well, it has many ingredients. So first you have to show that that x that you produced actually fits into the same class of deformation problems. So with Mark, I defined a long time ago the notion of divisorial Lac deformations, and we showed that it has a good deformation theory. But that's not obvious for an analytic approximation. You need to show that up to, when you have something that agrees up to a finite order, that it actually is a divisorial Lac deformation. That's a technical result. It's difficult, haven't proved it. So there's a paper on the web in December, and then you get this toric finite determinacy. And then if we use a criterion that we found in an unpublished book by Buford and Flanagan. Buford unfortunately died last year. That says, it gives a criterion of when something is a Hull if the base is smooth. You need to show that the Caloris-Spencer map is an isomorphism. So that's the last step. For this, again, you need to show that certain affine cohomology rules, and you work it out, and you see it's fine. Okay? So, of course, that leaves the question, that's for the situation that we know that not everything fits into. What's the situation in general? There should be some other method to prove that the mirrors you construct for integral symplectic forms are actually analytic. Okay? For the future. Thanks.
Thank you. Questions?
So, how do you avoid proving a convergence statement?
Essentially set it, right? Well, here, the approximation, that's a hard theorem, right? We use Duadi-Grauert, that we have a versal deformation. There exist analytic versal deformations. Okay?
Okay.
And then we use that there exist such deformations that agree to any given order. They have the same base spice and agree to any given order with a given deformation. Okay? So we never prove a convergence result.
Yeah.
We just say, okay, general machinery gives us such a versal deformation in analytic geometry. Hard result from 1970 or so. And then we compare. We complete the thing and say, okay, the completion of this thing is actually our family.
So the comparison in your theorem, this isomorphism, could be arbitrarily non-convergent. whatever formula you have to write for that.
What does this even mean?
Yeah, no, but
Your power series that you have to use there can have very.
What do you mean? I mean, the base is fixed. It's an isomorphism of the base.
No, but if you are controlling the close at each stage, I mean, you are basically reproving Artin's approximation in your situation, right?
We are using Artin's approximation.
But you're really reproving it if you're checking it order by order, the way he proves convergence is by adjusting the tails order by order.
Yeah, but
So
we
if
never
you're checking
use.
that they are compatible order by order, you are proving convergence.
I mean, that goes in this kind of, the Artin approximation theorem goes in and saying, okay, there is such an approximation from Duadi-Grauert that agrees to a given order with what we have. That's where we use Artin's approximation theorem. Fiber-wise, yeah, of course, you have big charts and they're far too big. That won't converge analytically. So the charts, these kind of toric charts, they are obviously wrong.
Other questions?
It's not a question, just remark, it's not directly related, but it's reminding me because you remove things of codimension too, in sense, yeah, and interesting periods of the complement. There was a story, almost forgotten now, Calabian's threefold, and remove finitely many rational curves, start to deform the formula, you get a big modular space, and eventually it will be like, you can contract curve and it will resolve singularities, and we get things like connected sum by 3 crosses 3, very non-algebraic, open pits of some non-algebraic threefolds by this game, and this is a big conjecture. For example, go to examples that modular space actually get algebra-driven
Yes.
structure.
Yes.
Something coming from high-dimensional form.
Yes.
Yeah, so I don't know whether that one can be used in some way.
Right. Yeah.
More comments? So let's think back again. We'll resume at 11.